In the first lesson, we have learned how to name aldehyde, ketone, and ester. So in this lesson, we're going to summarize all the organic compounds we have learned so far. And then we're going to discuss what are the properties they have in common and some of the properties that's unique to some of the organic compound. Okay, first of all, let's discuss some of the parts that we need to pay attention when we name those organic compounds. Okay, so here it lists out all type of organic compounds that we have learned so far. We have alkene, alcohol, aldehyde, ketone, carboxylic acid, and ester. Okay, so let's write out a functional group, and also is it necessary to write or mention the position of the functional group when we name that compound. For alkene, remember the functional group is a CC double bond. Okay, and for the CC double bond, we usually need to mention the position of the functional group. We don't mention it if it only got one possibility to put the double bond. Okay, and for alcohol, the functional group is the OH group. Okay, and for this OH group, it can be placed at any position along the carbon chain, so its position must be mentioned in the name. The next one, aldehyde. So the aldehyde, the functional group should be C double bond to O, and then it should be at the end of the carbon chain. Okay, so because it can only be attached at the end of the carbon chain, so there is no need to mention the position of the functional group. However, on the other hand, we have ketone. Again, it has a C double bond O as a functional group, the carbonyl group, but this time it must be placed in the middle of the carbon chain, and the position can vary. Okay, so we need to specify the position of the C double bond O, the carbonyl group. Next one, carboxylic acid. So the functional group is C double bond to O and then an OH group attached to it. Again, for carboxylic acid, it's similar to aldehyde. The functional group can only be placed at the end of the carbon chain, so there's no need to mention the position. Okay, and finally we have ester. So the functional group for ester is C double bond to O and then single bond to an O, and then this O would be further attached to an alkyl or aryl group. So for ester, again, there's no need to mention the position of the functional group because ester is formed by joining an alcohol and a carboxylic acid. So by mention these two original molecules' name in the name of the ester, we can work out the position of the functional group. Okay, so that's for this page. And then if we move on to the next page, this table focuses on comparing the intermolecular forces of different organic compounds. Okay, so there are four columns we need to fill in. So the first one is whether hydrogen bond can form between the molecules itself. Okay, so for example, we may have methane, and then can hydrogen bond be formed between two methane molecules? Okay, that's what we are looking for this column. And then the second one, we need to discuss whether this is a polar molecule or not. Okay, so if it's not a molecule, then we can put a tick for non-polar molecule. Okay, and then the last column we're going to discuss, will hydrogen bond formed between the molecule and the water molecule? Again, using the example I mentioned just now, if we have methane as an example, can hydrogen bond be formed between a methane molecule and a water molecule? If no, then we just put a cross here. And why do we care about those intermolecular forces that may be formed, because it plays an important role when we discussing its physical property, like whether it's water soluble or not, and whether it has a high boiling point or not. Okay, so let's fill in this table together. So the first one is already filled in for you, alkane, and by using the example I just mentioned, okay, methane, so there's no hydrogen attached to those most electronegative atoms, so of course there's no chance for hydrogen bond to be formed between those molecules. Okay, and since for alkane, okay, it doesn't include haloalkane here. Okay, so for alkane molecule itself is just non-polar. It only considers CH single bond and is symmetrically arranged, so it's non-polar. Okay. So move on to the next one. We have haloalkane. For haloalkane, remember the general formula we have is R attached to an X, and this X can be fluorine, can be chlorine, bromine, or iodine. Okay, so only fluorine is one of the top 3 most electronegative atoms. But for the first one, can hydrogen be formed or not between the molecule itself? So the answer is no, because we only have fluorine, which got lone pair on it, but we don't have any hydrogen that attached to this most electronegative atom. Okay, so no hydrogen bond can be formed between the molecules. And then we're going to consider whether haloalkane are polar or non-polar. So if we consider majority of the case, because it contains a polar bond, which is carbon, to these halogens, then it will form polar molecule. But of course, there are some special case. If we have those halogens attached onto the carbon chain symmetrically, then it can be nonpolar. Okay, and then can hydrogen bond be formed between the molecule and water molecule? Okay, so there is one possibility. So for most or majority of the case, we say no, but only except that we have R attached to a fluorine. Okay. Okay, and then move on to the next one, alkene. So for alkene, the functional group is CC double bond. Okay, so again, there's no O and F presented in it, so it would not be able to form hydrogen bond between the molecules, and because it's symmetrically arranged, all the atoms are symmetrically arranged, so it will be non-polar for alkene. And since it doesn't have any O and F in it, and it won't be able to form hydrogen bond between the molecule and water molecule. Okay, move on to the next one. Next one, we got alcohol. So alcohol, remember the functional group? We got OH. Okay, so here, it got an H, okay, that's attached to the most electronegative atom O and F, okay, and also it got lone pair on this oxygen. Okay, so when we have 2 alcohol molecules together, they can form hydrogen bond. Okay, and then the next one, whether it's polar or non-polar, because the OH bond attached to this alcohol, so it will make it polar. Okay, and when alcohol meet other water molecule, it would be able to form hydrogen bond. Okay, so it got lone pairs on oxygen of the alcohol and oxygen on water, and also it got hydrogen attached to oxygen on both alcohol and water, so it can form hydrogen bond. Next one, we got aldehyde. So for aldehyde, here, remember the functional group we have is like this. Okay, so here we got oxygen, which have lone pair on it. Okay, let me make my oxygen a full circle. Right, so for this oxygen, yes, it has lone pair on it. However, we don't have any hydrogen that directly attached to oxygen. Okay, so within this molecule itself, it cannot form hydrogen bond. Okay, and because this symmetrical structure, it must be a polar molecule. And then, can aldehyde form hydrogen bond with water? Okay, the answer is yes. Okay, so because the oxygen from the aldehyde got lone pairs on it, and it can form hydrogen bond with the hydrogen from the water. Okay, and for ketone, again, since it doesn't have any hydrogen attached to those most electronegative atoms, so it would be no. Okay, it cannot form hydrogen bond between the molecules. And again, because it's not symmetrically arranged in its structure, so it's a polar molecule. And similar to aldehyde, it can form hydrogen bond with water molecules because it got this oxygen that has lone pair on it. The next example, we have carboxylic acid. Okay, so the functional group for carboxylic acid is C double bond to O, and then we got O and then H. So here we got two oxygen that have lone pairs on it, this one and this one, and we also have hydrogen that directly attached to oxygen. So within the molecule of carboxylic acid, it can actually form hydrogen bond. And because of this special structure, it's not symmetrical, so it's a polar molecule. Okay, and it can form hydrogen bond with water, quite straightforward. Okay, so the next one, we got ester. So the functional group for ester, let's write it out. It's this one. Okay, so we got oxygen that have lone pairs on it. But we don't have any hydrogen that attach to those oxygen. So between ester molecule itself, it cannot form any hydrogen bond. Okay, and again, because its structure is not symmetrical, so it's a polar molecule. And lastly, can it form hydrogen bond with water molecule? The answer is yes, because it got those oxygen that have lone pairs on it. Okay? So why do we need to summarize this table? How can this table help us to predict the physical properties? Okay, first take a look at the first three columns. So in this three columns, we consider what kind of intermolecular forces going to be present within the molecule. If it can form hydrogen bond between the molecule, so it would have the strongest intermolecular forces. Hence, if we're talking about its boiling point or the melting point, it's going to be the highest if it can form hydrogen bond, okay, within the molecule, then it's going to have the highest boiling point or melting point. And then the next one, if it's a polar molecule, then we say it would have a stronger van der Waals forces between molecules. So we say it would have a medium boiling point or melting point. If it's nonpolar, of course it cannot form any hydrogen bond within the molecule, then it will have the lowest boiling point or melting point because it only have weaker van der Waals forces between the molecules. In the last column, can hydrogen bond be formed between between this organic molecule and water molecule? That's to tell you whether it can dissolve in water or not, okay? Whether it's water soluble or not. Okay, so you can see for the parts that we put a cross in it, that means it's insoluble. Okay, so for alkane and alkene, we have seen samples in the lab, they are insoluble in water. And for haloalkane, they are slightly soluble. Slightly soluble. Okay, and this is because of the polar bond that it contains. Okay, it's because the polar RH bond within the haloalkane molecule. Okay, so for haloalkane, it's slightly soluble, and for those we put a thickener, okay, that means these organic compounds can all dissolve in water. Okay, so we complete this part, and then start from the next page, I'm going to teach you how we can compare the solubility and boiling point, and how are we going to answer those questions. Okay, there are some format and some keywords you must remember in order to get the marks. Okay, so first, the water solubility. Okay, so of course, when the molecule can form hydrogen bond to water molecule, it's gonna be highly soluble in water. And then the next one is for polar molecule. If it's non-polar molecule, it's gonna be the least soluble substance. And then for explanation, we can say molecules with longer carbon chain will have a lower solubility, as carbon chain is nonpolar and shows hydrophobic character. Okay, hydrophobic means it's gonna repel water. Okay, in order to attract water, it needs to have stronger forces, right? Okay, so that's why we are looking for hydrogen bond for those very highly soluble substance. And the longer the chain, the stronger the hydrophobic character from the carbon chain. Okay, so it's gonna be less soluble. That's for the first part, water solubility. And then the second part, sometimes we may also need to compare their boiling point. Okay, and again it will follow this order. We need to first consider whether hydrogen bond can occur within the molecule, and then the next factor, whether it's polar or not, and then if it's not if it's non-polar, it's gonna have the lowest boiling point. Okay, and after that, if it's non-polar molecule, then we further need to compare the size. Okay, as the size of the carbon compound increase, the strength of the van der Waals forces also increase. And due to the stronger intermolecular forces, more heat gonna be needed to separate the molecules during boiling, and thus the boiling point increases. Okay, so when comparing boiling point, first consider hydrogen bond or not, second polar or not, and third the size. Okay, similar to the parts that we compare purely the intermolecular forces. Okay, here we got some examples. In this table, it lists out all the first few primary alcohol, okay, with one hydroxyl group only. Okay, so there's only one OH group in here. and you can see the trend. Okay, as we go down this table, we can see the carbon chain gets longer, and then also the boiling point, okay, gets increased here, get higher, and the water solubility, okay, and decreased. Okay, so using the factor that we have discussed on the top part of this page, we could be able to conclude the reason. We will be able to explain why this trend can be found. Okay, so as all of the above alcohols can only have one hydroxyl group, so each of the molecule can only form one hydrogen bond. Okay, so the first factor doesn't really affect the trend that much. Okay, so we skip the first factor, and then the second one, okay, whether they are polar or non-polar. For alcohol, they are all polar. Okay, so the second factor won't contribute a lot here. And then we move on to the next one. We need to compare the size. Okay, as we go down the table, the carbon chain gets longer, so the size increases. Okay, and with larger molecular size, that will result in a stronger van der Waals forces. Okay, and the stronger van der Waals forces means it would have higher boiling point. Okay, that's the first effect. And then the second one, since the carbon chain have increased, the hydrophobic effect from the carbon chain also increase. Okay, so we have a longer nonpolar carbon chain that will reduce the water solubility of the molecule. Okay, so that's why we found these two trends on this table. Here we got another example. Okay, this table lists out the first 6 carboxylic acid. Okay, and again, as we go down this table, the carbon chain increased, the boiling point also increased, and then the solubility decreased. Okay, so how do we explain this two trend? Okay, again, for the water solubility, you can see the first four in this group, they are soluble in water. Okay, but larger one, okay, so if the carbon chain contains 5 or more carbons in it, they are less soluble. Again, it's due to the hydrophobic nature of the alkyl chain attached to the carboxylic functional group. Okay, so you must remember these parts. That's very important. The first 4, they are soluble in water, and the longer chain, they are less soluble. And then for the boiling part, easy to explain. As we go down the group, the size increase, the size of the molecule increase. That results in stronger van der Waals forces. Hence, the boiling point increase. But here, I also want to point out we can compare the boiling point, okay, with the alcohol. Okay, so if we take one example, if we take alcohol, so ethanoic acid and ethanol. Okay, so let's circle it out. Ethanoic acid is here. Right, so boiling point is 118, but for ethanol, we have here the boiling point is 78. So why do ethanoic acid have has a higher boiling point than ethanol? Okay, so this part is important because for carboxylic acid, it can form something called a dimer. Okay, due to its tendency to self-associate. Okay, remember the structure for carboxylic acid. okay, is 120 degrees here. Okay, so make it flat, and then we also have 120 degrees here. So it will make it perfectly aligned to form hydrogen bond to each other. Okay, so two of the carboxylic acid molecule will be joined together, and hence it form a dimer which got a larger size. Okay, so it would form stronger intermolecular forces, and it will increase the boiling point. Okay, so if we circle the keywords here, this immediately doubles the size of the molecule since it forms dimer. Okay, and therefore it will increase the strength of the van der Waals forces between the molecule, and then it will result in higher boiling point. Okay. So here are some checkpoint questions. I want you to pause the video here, try to complete the questions by yourself, and then check your answer with me. So take a look at the first one. Okay, the following compounds are arranged in order of increasing boiling point. Explain your answer. Okay, so here we got a carboxylic acid, and then followed by an alcohol, and followed by two haloalkanes. Okay, so first we describe the change. The boiling point of the substance increase, and we also know the boiling point of the substance depends on the strength of intermolecular forces. Okay, and then we need to consider the first factor, whether it can form hydrogen bonds between molecules. Okay, so as we can see, only alcohol and carboxylic acid it will be able to form hydrogen bond between molecules. Right, so we first mentioned that. Okay, so only these two can form hydrogen bonds between molecules, so they have the higher boiling point. And then we need to further compare the carboxylic acid and the alcohol. And as we mentioned on the previous page, for carboxylic acid, they can form a dimer between the molecule. Okay, so the dimer causes the increase in molecular size. Okay, hence, and also the more intensive hydrogen bond between the molecule. So both factors result in a higher boiling point of the carboxylic acid compared to the similar sized alcohol. And then for the last two, they are haloalkanes. So they are both polar molecule. So we need to move on to the last factor we need to consider, which is molecular size. And we know bromine is larger than chlorine. So this molecule with bromine in it has a larger molecular size than the one with chlorine. Okay, so the larger molecular size would result in greater van der Waals forces. Between molecules, and therefore this molecule would have a higher boiling point than this one. Okay, that's how we compare the boiling point between those molecules. Okay, then move on to the second question. It involves calculation. Compound W contains carbon, hydrogen, and oxygen only. the relative molecular mass of W is 72. Complete combustion of 1.44 gram of W gives 3.52 gram of carbon dioxide and 1.44 gram of water. Okay, deduce the molecular formula of W. So in order to work out the molecular formula, we first need to work out the empirical formula. Okay, and we can write the chemical equation. When complete combusted, it should only give out carbon dioxide and carbon dioxide and water as the product. Okay, so by using the percentage by mass, we can work out the mass of carbon produced or involved in this reaction, and the mass of hydrogen that involved in this reaction. I'm sorry that the format changed a little bit. Okay, so for here, do you still remember how do we calculate percentage by mass? Okay, so in order to find out the mass of carbon, we would need to work out the percentage by mass of carbon in it, so which should be 12 over the molar mass for the whole thing, which is 12 plus 2 times 16. Okay, and since it produced 3.52 gram of carbon, then we multiply by the total mass, then it will give us a mass for carbon. It should be 0.96 gram. Okay, so we use the same principle. We can work out the mass of hydrogen. Okay, so the percentage by mass of hydrogen in water is 1.0 times 2. There are 2 hydrogen atoms, and then over the total mass. Total molar mass. Okay, 1.0 times 2 plus 16. Okay, and that's a percentage by mass. That's how much hydrogen atoms are weighed in the water molecule. Okay, and then times the total mass, and then it will give us the mass for hydrogen only, okay, which is 0.16 gram. Okay, so if we know the mass for carbon and we know the mass for hydrogen, and we also know the total mass for W, and then the only thing left with is oxygen. Okay, so we can work out the mass for oxygen, which is 1.44 minus 0.96, which is the mass of carbon, and minus 0.16, the mass of hydrogen. So that will give us 0.32 gram. Okay, so if we now have the mass for all 3 elements, then we can work out number of mole and compare their mole and work out the mole ratio. So for carbon, it should be 0.96 over 12. And for hydrogen, it will be 0.16 over 1.0. And for oxygen, it will be 0.32 over 16. Okay, and then we work out the answer. It will become 0.08 to 0.16 to 0.02. And to simplify this, we want to work out the whole number ratio. So that will be, and then we should divide it by the smallest number, okay, which is 0.02 here. So 0.08 divided by 0.02 would give us 4. And for this one, it would give us 8. And then, of course, 0.02 divided by itself, it will give 1. So the whole number ratio will be 481. So the empirical formula for W will be C4H8 and O. Okay, so now we have worked out the empirical formula, and remember in the question it tells us the relative molecular mass is 72. Okay, so that means a number multiplied by the molecular mass for the empirical formula, it should give 72. So that would be 12 multiplied by 4 plus 1 multiplied by 8 plus 16 and give us 72. And if we solve that equation, and we will work out n actually equals 1. So the molecular formula is actually C4H8O. Okay, so next part. Given that W has only one functional group, so draw two possible structures of W and give their IUPAC name. Okay, so look at this formula. First, it contains one oxygen. Okay, so we can consider it to be an aldehyde. Okay, and if it can be aldehyde, then it can also be ketone. Okay, so we can draw these two possibility first. Okay, it got 4 carbon. Okay, so we put 4 carbons in it, and for aldehyde, the oxygen would be placed at the end, double bond to O, and then fill in the rest. Okay, so then we give the IUPAC name for this. The longest carbon chain got 4 carbons in it, so it will be butanol. Okay, and then we can move the C double bond O group, carbonyl group. Okay, and so in the middle, maybe we put it here, and then we fill in the rest. Okay, so that will give us butanol. Okay, and for this one, there's no need for us to mention the position. So as if we move the C double bond O to here, then we start to count our carbon from this side, so still the same position. Okay, and then we move on to the next question. Okay, so next one. Molecule X has molar mass 88 gram per mole and found to contain 54.5% of carbon, 9.1% of hydrogen, 36.4% of oxygen. Okay, what are the empirical formula and molecular formula? Okay, so using the same way that we have done in the first question, okay, we first label all the elements. We have carbon, hydrogen, and oxygen. And then first we write out the percentage by mass. Okay, so carbon contains 54.5, hydrogen contains 9.1, oxygen has 36.4. So imagine we have 100 grams of this molecule, okay, and then the number of mole would be 54.5 over 12, and for hydrogen it will be 9.1 over 1. For oxygen it's going to be 36.4 over 16. Okay, and then we work out the answer. It will be 4.542, and that would be 9.1, and that would be 2.275. And then we need to work out the ratio, whole number ratio. And you can see it's roughly 2 to 4 to 1 ratio. Okay, so the empirical formula is C2H4 and O. Okay, and then we know the molar mass is 88 gram per mole. So that means N times 12 times 2 plus 1 times 4 plus 16, which is the molar mass for the empirical formula. And after it multiplied by those by number n, it should give us 88. So to solve that equation, then we can get n equals 2. So our the molecular formula is the empirical formula multiplied by 2, C4H8O2. Okay, and then for part B, okay, given the molecule X has only one functional group, draw two possible structures of X with different functional groups, and give their IUPAC name. Okay, so now it got 2 oxygen in it, so we can consider the 2 type of molecule we have learned that got 2 oxygen in it. The first one is an ester. Okay, so just draw one possible structure for it. Okay, we can have since it got 4 carbon, we can have 1 carbon and then 2 O, and then 3 carbon on the other side. Okay, and then we fill in with those hydrogen. Okay, so to name this, remember we break it into 2 parts. We name the alcohol part first and then the carboxylic acid part. So the alcohol part is a methyl group. It's a methanol. Okay, and for the carboxylic acid part, it got 3 carbons in it. So it's propanoic acid. So we change the ending, it will become propanoate. Okay, that's one possibility. And how about the other one? Okay, we can make it a carboxylic acid. Okay, so for carboxylic acid, it will be placed at the end of the carbon chain. Okay, and then we'll fill in the hydrogen that's needed. Okay, so for this molecule, it got 4 carbons in the carbon chain, so that's butanoic acid. Okay, and then finally for this part, there are some common trivial names for the carbon compounds that you need to be familiar with. Okay, so take a look through this page and try to get familiar with those names.